Welcome back to the course Computer Graphics. In the last video we have seen the introduction to image processing. Here we are going to see the relationship between pixels and the image representation, digital image representation. Okay, so first we will see the digital image representation. An image can be defined as a two-dimensional function f of xy, where xy is the spatial coordinates, the function f is the amplitude of any pair of coordinate xy, which is called the intensity or gray level of the image at that point, and x, y and f are all finite and discrete quantities. So that means an image can be defined as a two-dimensional function, which means it can be arranged in rows and columns. Okay, so at the beginning the sensor captures the image in this format. The continuous image projected onto a sensor array will be like this, and after performing sampling and quantization techniques on this original image, you get a digital image like this, and this can be represented as a two-dimensional function f of xy. Okay, and the digital image is composed of a finite number of elements, each of which elements have a particular value at a particular location, and these elements are referred to as picture elements or image elements or pixels. That means this in this image, which is converted using image sampling and quantization, each of these positions, they are the elements. Each element of this image is called as image elements or pixels. Commonly the widely used term is pixel. So every image will be consisting of a finite number of elements, and each of this will be called as a pixel. Okay, based on this there will be mainly four type of images are there, that is binary image, black and white image, 8-bit color format and 16-bit color format. Binary image means there will be it contains only two kinds of pixel elements, that is 0 and 2 pixel elements, that is 0 and 1. That is 0 refers to black and 1 refers to white, and such image is called a monochrome image also. So it is basically known as binary image or monochrome image. Okay, then second type of image is black and white image. Black and white image means it consists of only black and white colors. Okay, and the third type is 8-bit color format, which is a very commonly known format, that is grayscale image. Okay, so in this grayscale image, 256 different shades of colors are possible. The 0 stands for black, 255 stands for white, and 127 stands for gray. Okay, so that is 8-bit color format. And finally 16-bit color format. 16-bit color format, it's again a color image format. It is known as high color format, that is it has 65,536 different colors in it, and in this format the distribution of colors is not same as that of grayscale image. And in 16-bit color format, it is further divided into three formats, that is red, green and blue, that is the very famous RGB format. Okay, so these are the different types of images possible, and the images can be represented as a matrix like this. Okay, so the images are represented in rows and columns. That is here f of xy, the image f of xy is represented as a matrix. Here each of these elements are the pixels. Okay, so f00 is the intensity value of the image at that coordinate 00, the coordinate 00. F00 is the intensity value of that image at the coordinate position 00. So this 00 position is one pixel or one picture element. Similarly, each of this f01, f02, fm-1, n-1 all are pixels or picture elements, and these are the intensity values of the pixels at that particular position. Okay. So this is how you represent a image using as a matrix. And in image processing, what happens is it typically defines a new image G in terms of an existing image F. That is, it can transform either the range of F, that is G of F x y equal to transforming f of xy, t of f of xy, or you can also transform the domain of f itself, that is g of xy will be equal to f of tx xy ty xy, that is the domain will be changed. Okay, so in image processing, it defines a new image G which in terms of an original image or an existing image F. Okay, that is what is happening, actually happening in digital image processing. Okay, then that is all about the image representation. Now we are going to see the relationship between pixels. The relationship between pixels can be shown using different terms in image processing. So first one is neighbors of a pixel. Neighbors of a pixel can be 4 neighbors of P or 8 neighbors of P or uh, uh, or diagonal neighbors of P. Okay, so 4 neighbors of P. 4 neighbors of P means a pixel P at coordinates xy has 4 horizontal and vertical neighbors, that is 2 horizontal and 2 vertical neighbors whose coordinates are given by x plus 1 y, x minus 1 y, x y plus 1, x y minus 1. That is, if you see this image, you can understand. If this x y is the pixel P, then this P has 4 neighbors in the horizontal and vertical direction. See, so these are the gray colored pixels are the 4 neighbors of P, and these are denoted by n4 of P, n4 of P. Okay, so each pixel is 1 unit distance from xy, and some of the neighbors of P lie outside the digital image if xy is a border of the image. If this is a border of the image, if it is one border of the image, it can lie outside the image also. The neighbor can lie outside the image also. Then that was about 4 neighbors. Similarly, there were 4 diagonal neighbors also. These are, if you see this image, you can understand these pixels which are diagonal to this pixel P at position xy are called the diagonal neighbors, and it is denoted as nd of P. That is the pixel x minus 1 y minus 1, x minus 1 y plus 1, x plus 1 y plus 1, and x plus 1 y minus 1. These pixels are called the diagonal neighbors of P, and these points together with 4 neighbors of P are called 8 neighbors of P. That is, all these 8 pixels around this pixel P are called the 8 neighbors of P, and it is denoted as N8 of P. Okay, and as we have already told before, if xy, that is P, is in the border of the image, then these neighbors can lie outside the image. Okay, so that is about the neighbors of a pixel. Then next type of relationship used in a case of pixels is adjacency and connectivity. First we will see adjacency. Before going into adjacency, we will see a set V. V is a set of intensity values that is used to define the adjacency and connectivity. That means when we talk about adjacency and connectivity, we will be defining it based on some kind of defining it based on a set. Okay, so if in case of a binary image, if V is equal to a set with value 1, if V is equal to 1, then we are referring to adjacency of pixels with value 1 only. Okay, so binary image means it consists of only zeros and ones, and if the value of if V is taken as 1, that is V is taken as the set 1, means we are going to we are referring the adjacency of pixels of only the set 1. That means only the element pixels with value 1 will be taken to check for adjacency or connectivity. Okay, so in case of grayscale image also this thing is same, the idea is same, but here instead of V is equal to 1 or V is equal to 0, here this set V can contain more number of intensity values. Okay, so like an example, V can be a set with values 180, 181, 182 to 200. So it can be in case of a grayscale image, it can be any intensity values between 0 and 255. Okay, any subset of these 256 values can be V. Okay, so this adjacency and connectivity will be always defined based on this set V. Okay, just keep it in mind. So if you see adjacency of pixel, there are 3 type of adjacencies possible, that is 4 adjacency, 8 adjacency and M adjacency. 4 adjacency means 2 pixels P and Q are with values V are 4 adjacent if Q is in the set N4 of P. That means if you take this image, that is if xy is P and if Q is any of this N4 neighbors, okay, this N4 of P, if Q is any of this, then it is 4 adjacent. Okay, then P and Q are 4 adjacent. Okay, so if this is P and Q is this, then this P and this Q are 4 adjacent. Okay, similarly 8 adjacency. 8 adjacency means if this is P, if this xy is P, any of this 8 pixels can be, if any of this 8 pixels is q, then it is 8 adjacent. Okay, so if this is p, then and if this is this x minus 1 y minus 1 is q, then that means this x minus 1 y minus 1 and xy are 8 adjacent. Okay, and you have M adjacency. M adjacency means it is a mixed kind of adjacency, that is 2 pixels p and q with values v are M adjacent if q is in the n4 of p or in nd of p, and the set n4 of p intersection n4 of q has no pixels whose values are from v. That means if you take this image again, if this is p, then either this n4 of p can be taken for adjacency or nd of p can be taken for adjacency. Nd means these diagonal neighbors can be taken for adjacency. Any of these will be taken for adjacency, and also you have to check that is the 4 neighbors of p and 4 neighbors of q. When the 4 neighbors of p and 4 neighbors of q are taken and perform intersection, no pixels with no pixel, there will not be any pixels whose values are from v. Okay, that means there is no intersection possible. Okay, then it is M adjacent. Okay, so that is a mixed kind of adjacency. Okay, so you can see the difference of 8 adjacency and M adjacency here. Actually, the M adjacency or mixed adjacency is a modification of 8 adjacency. It was introduced to eliminate the ambiguities that often arise when 8 adjacency is used. That is, if you take the adjacent elements of 8 adjacent elements of a central pixel, this is a pixel representation. If you take this center pixel, the 8 adjacents of the center pixel for v equal to 1 will be this one, and this one. So, okay, so this way adjacency is possible, this way adjacency is possible, this way adjacency is possible. Okay, so that is there are multiple paths between two pixels, right? Between these two pixels, the central pixel and the top right pixel, there are multiple paths. But in M adjacency, you either take diagonal elements or either nd of p or n4 of p will be taken. Okay, q is in either n4 of p or q is in nd of p, and n4 of p intersection nq of p will be that means there is no intersection between n4 of p and nq of n4 of q. Okay, so then there will be only a single path between these all of these pixels. Okay, so in M adjacency, it has eliminated the multiple path connection that has been generated by the 8 adjacency. Okay, so another term used in case of relationship between pixels is the digital path. A digital path or a curve from pixel p with coordinate xy to pixel q with the coordinate st is a sequence of distinct pixels with coordinates x0, y0, x1 y1 to xn yn, and here the x0 y0 and xn yn will be p and q respectively, and xi yi and xi minus 1 yi minus 1 are adjacent for 1 less than or equal to I less than or equal to n is the length of the path. Okay, so this will be the length of the path, and if x0 y0 is equal to xn yn, that means if p is equal to q, that means the path is closed. It is a closed path. Okay, so a digital path means simply if you have a pixel p with coordinate values x, y, and if you have a pixel q with coordinates st, if you draw a path from p to q, this path is the pixels which lie between this p and q, and it can be coordinates x0, y0, x1, y1, x2, xn, yn, and here x0, y0 will be the initial pixel p and xn, yn will be the final pixel q, and if x0, y0 is equal to xn, yn, that means it is a closed path. There will be that means it begins and ends at the same point, same pixel. Okay, so we can specify 4, 8 and m paths depending on the type of adjacency we are specifying. Okay. So this is an example of a digital path. If you can see the 8 adjacency or in a 8 path. Similarly, an m path is shown here for v equal to 1. Okay, so that's about digital path. Then connectivity. If S represents a subset of pixel in an image, then two pixels P and Q are said to be connected in S if there exists a path between them consisting entirely of pixels in S. Okay, so then it is called a connected pixel. Okay, two pixels P and Q are connected in S if there is a path between P and Q which entirely lies which are entirely consisting of pixels in the subset S. Okay, and for any pixel P in S, the set of pixels that are connected to it in S is called a connected component of S, and if it only has one connected component, then set S is called a connected set. Okay, so that is about connectivity. Then we will see some region and boundary of pixels. Okay, region, a subset R, if it consists of a subset of pixels in an image, we call R a region of the image if R is a connected set. Okay, so R is a subset of images, subset of pixels in an image, then this R is called as a region if R is a connected set of pixels. Okay, and if there are two regions Ri and Rj, they are said to be adjacent if their union is a connected set as well. Okay, and if it is not adjacent, then means they are disjoint regions. Okay, then boundary means if you have a region R and if you take the complement of R, then the boundary of region R is the set of points that are adjacent to points in the complement of R. That is, simply the border of a region is a set of pixels in the region that have at least one background neighbor. Okay, so if you take an image, the border will be having a set of pixels which 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 has neighbor in the background image. Okay, so that is boundary. And if R happens to be an entire image, then its boundary is defined as a set of pixels in the first and last rows and columns in the image. And this extra definition is required because an image has no neighbors beyond its borders. Normally, when we refer to a region, we are referring to a subset of an image, and any pixel in the boundary of the region that happens to coincide with the border of the image are included implicitly as part of the region boundary. Next is distance measures. Uh, that is a measure of distance between two pixels PQ. So for pixels P, Q and Z with coordinate x, y, s, t and v, w respectively, d is a distance function if d of pq is greater than or equal to 0, d of pq is equal to 0 only if p is equal to q, then d of pq is equal to d of qp, and d of pz is less than or equal to d of pq plus d of qz. So the Euclidean distance between p and q is defined as dE of pq. dE of pq is a distance function which is measured using Euclidean distance. So d of pq is equal to root of x minus s the whole square plus y minus t the whole square. So here x, y are coordinates of pq, p, xy is the coordinate of p, and st is the coordinate of q. Okay, so from this two values, from this coordinate values of p and q, you can find the distance between p and q, the pixels p and q, using Euclidean distance equation, that is root of x minus s the whole square plus y minus t the whole square. Pixels having a distance less than or equal to some value r from xy are the points contained in the disk of radius r centered at xy. Okay, so if we have a pixel xy, uh, all the points with a distance less than or equal to r are points contained in a disk of radius r centered at xy. That means if you have a pixel uh, and if you have to find a pixel with a distance measure r from xy, there can be many points within the radius r centered at xy with this with the distance measure less than or equal to r. Okay, then d4 distance, it is also called city block distance. City block distance between two pixels p and q is defined as d4 of pq, which is equal to x minus x, x minus s plus y minus t. Okay, so the pixels having d4 distance from xy less than or equal to some value r form a diamond centered at xy. That is, if you see this example, you will understand. So, if the pixel having d4 distance from xy less than or equal to some value r, then so here the value of r is 2, that is d4 distance is less than or equal to 2, all the pixels with this distance they are less than or equal to 2 from the the pixel with the coordinate xy form the following forms a diamond like this. So here the distance is less than or equal to 2, so it forms a diamond which is centered at xy. So here this 0 is the pixel with the coordinate xy. The pixel with d4 equal to 1 are 4 neighbors of xy. So here pixel with the d4 is 1, this is d4 1, which is the 4 neighbors, and with the 2 is the next 8 neighbors. Okay. Next is d8 distance. D8 distance is also called chessboard distance between two pixels P and Q, and it is defined as D8 of PQ, which is equal to maximum of x minus s and y minus t. Okay, so again xy is the coordinates of P and Q having the coordinates st. Okay, so you have to take the maximum of x minus s and y minus t. So pixels having a d8 distance from xy less than or equal to some value r form a square centered at xy. For d4 distance it was forming a diamond. Here it will form a square. Okay, so here is an example. For d8 distance less than or equal to 2 from xy, form a square centered at xy. Then next is dm distance. Dm distance is defined as the shortest m path between the points. In this case, the distance between two pixels will depend on the values of the pixels along the path as well as the values of their neighbors. Okay, so here is an example. Here you have to consider the following arrangement of pixels. This arrangement of pixels. Assume that P, P2, P4 have value 1 and P1, P3 have a value of 0 or 1. So we consider the adjacency of pixels values 1. Okay, here we are going to consider only the adjacency of pixel value 1. P, P2, P4 have value 1 always. P1 and P3 can have a value of 0 or 1. So based on this there will be 4 cases. Case 1 where P1 is equal to 0 and P3 is equal to 0. If P1 and P3 is equal to 0, this will be the arrangement of pixels. Then the length of shortest m path, that is dm distance, will be equal to 2, that is P, P2, P4. So that will be the distance, that is 2. Yeah. Next case, P1 is equal to 1 and P3 is equal to 0. So the uh, pixel pattern will be like this. Pixels will be arranged like this. So P1 1 and P3 0. Now P1 and P will no longer be adjacent. Then the length of the shortest path will be P, P1, P2, P4. So the distance will be 3. Then in case 3, P1 equal to 0 and P3 is equal to 1, then the same above will apply here also. So the shortest m path or dm distance will be equal to 3. Then finally P1 is equal to 1 and P3 equal to 1, the length of the shortest M path, that is DM distance, will be from P. P will be 4. That is P, P1, P2, P3, P4. So that will be the DM distance. So that is all about the distance measures. Thank you.